Good afternoon, everybody. My name is Andrew, now at least, and I'm here to talk about angr, which is a tool that we have developed to do static analysis and symbolic execution using VEX. Like I said, I am a researcher. I'm an undergraduate student at the University of California, Santa Barbara. We work in what we call the Sec Lab. We are, like most of the people in this room, interested in finding bugs in software. And because we are researchers, we are interested in publishing papers about finding bugs in software. The more automatic, the better in this case. And also, we are CTF players. CTF, as maybe some of you may know, is Capture the Flag. It's a computer security game. It's fun, you know. It's about taking the security tasks and making them into fun challenges that you can solve for points, occasionally money. But what we'd really like to do, as all these different categories of people, is have some way to perform binary analysis tasks in useful, modularizable, abstracted ways. And to that end, we have developed a system called angr. And angr is, the tagline is, a highly modular Python framework that performs binary analysis using VEX as an intermediate representation. In fact, the name angr is a pun on VEX, because when something is vexing, it makes you angry. Probably half of our code base is pun-based.
Is this true, or are you making that up?
Oh, no, that's totally true. The graphical interface for angr is called angr management. And so the idea of angr is that it is made of many interlocking parts which provide useful abstractions for analysis. So the first part of this presentation is going to be detailing the pile of abstractions that we call angr. So, interlocking part 1 is PyVex, which is effectively a FFI foreign functions interface wrapper around Libvex. So this is the bread and butter of all of our further analysis that we'd like to be able to do. We would like to be able to run a line of Python and have out a Python object which is the intermediate representation superblock, the IRSB, that contains the VEX IR code that is much more easily analyzed than just x86 bytes or ARM bytes or what have you. So the way we've done this is there's a whole lot of hacking into Libvex in order to actually get the IRSB object out, and then we deep copy it into a set of Python classes that represent the internal VEX structs that are easy to work with in Python. So you can just drill into an IRSB and say, well, what's the third statement's operation and what are its arguments, which are a read temp and a constant statement. Uh-oh. Oh, good. That's much better. Yeah. There we go. And technically, this can be totally independent of Libvex, the library, because we have an interface in which you can write lifters in pure Python, and we've done this for AVR, MSP430, and brainfuck. Yeah, no. So that's interlocking part number 1. Interlocking part number 4 is called SymVex. SymVex is, jumping ahead a little, the actual symbolic execution that we do with IRSBs. So I'll explain what exactly symbolic execution is in a moment and how exactly it works. But for now, you just need to know that it takes the IRSBs that we have generated via PyVex and executes them. But it technically supports execution from other interfaces that aren't VEX. SymVex has grown into be a little bit of a misnomer as we've grown and expanded the library to support more things. But VEX is the first and the best supported, and it's also in the name. So most important, if you're going to emulate IRSBs, you're going to need to emulate the effects of each of the kind of IR statements, expressions, operations, dirty calls, and clean calls. But ultimately, the abstraction that you get out of SymVex is this concept of a simulated state, which is a representation of a program state at a given time. And the symbolic execution process is one that produces, given a state, any number of successors that could possibly result from executing that state. So once we start thinking about executing things, we need to start thinking about the environment in which we execute things. So we need to start thinking about how do we model memory, how do we model registers. VEX has sort of decided the answers to those questions for us. We have a flat memory space and a flat register file. But other than that, you need to start providing, well, what happens when you hit the IJK sys and you need to emulate a syscall? What happens when, how do you actually model those syscalls and their events symbolically, and etc. So one of the things that we use to make this work whatsoever is this module called clarify in our locking part number 2. So Valgrind and its friends will want to use VEX and emulate these things, and in all the registers there will be integers. But what we want is we want not integers but symbolic bit vectors, which are effectively variables that can be built up into trees, and then you end up with ASTs of just variables and values and operations and then you can reason about, well, what if there were a constraint saying that this value must be greater than this value, and you just say that that is an assertion over the current program state. Then once that assertion is in place, you can use an SNT solver such as Z3 in order to reason about additional values that therefore must be a certain value given this constraint. So clarify is the abstraction layer that allows us to reason about bit vectors as well as integers as well as any number of domains that we will sometimes choose to use for static analysis. So as a brief interlude here, let's talk about what the actual process of symbolic execution looks like. So we're going to show you how symbolic execution executes a program and what we can do with that. And these slides are stolen from every single other presentation about angr ever. So pretend for a moment that we have this code slice. We don't even have to pretend, there it is. So we're going to start execution up here, the blue line, and we're going to start with a sort of blank state that contains that says that, well, we don't know what x is yet, and there's no constraints on this state yet, but we do know our instruction pointer is there. So when we tick forward, we're going to, I should have said, okay, so when I say x is question marks, what I actually mean is x is a symbolic value. That is, x is user input, and we don't have any idea, we don't have any conception of what that value could be, so we'll just create a symbol, x, and say that is x. Then, as we tick execution forward, we will hit that branch statement, and there are two possible places that the CPU could jump to after that instruction. It could either jump to here, or it could jump to here. And in symbolic execution, we take both. So this initial state produces two successor states, state AA and state AB. In it, x, we still have no conception about what the actual value of x is, but we do now have a constraint, an assertion over the domain of values that x may take on. That is, in this state AA, we know that x must be less than 10, and in state AB, x must be greater than or equal to 10. So then, so the process of SymVeX, the symbolic execution, is effectively computing this constraint, so it is extracting the idea of this constraint from the code and placing it in the actual state. So if we just sort of continue the example, we are now going to take the state AB, because that's the one that's getting us closer to the Llvm, because we're trying to win here. That's what we're here to do. So then state AB is going to further branch on the second if statement, and it's going to add add the constraints on the state x is less than 100, x is greater than or equal to 100. And so now we can say that state ABA is the state that ends up being at the Llvm spot. And we can tell that. So therefore, we just invoke a constraint solver on the value of x given those variables. And we end up with, well, there is a possible value of x that could, and does, cause the program to take that path. So that's symbolic execution. That's the goal here. So as sort of a side note, the third interlocking part, and a very out-of-order list of interlocking parts, is a binary loader that we implemented for the angr project. It's called Clay, stands for Clay Loads Everything. It's very complicated. Talking about it is not at all within the scope of the presentation, but it ought to be mentioned since it is important. It takes it does the job of a dynamic loader. It takes a library and executables and turns them into an address space. I did most of the work on that. It's very hard. Don't ever try to do that.
Don't copy your code.
So then interlocking part number 5, the last part, there's an infinite number of interlocking parts, but let's pretend that there's a finite number, so there's 5 of them, is angr, the actual top-level control module. So this takes all these abstractions and puts them together into a control interface called a project, which allows convenient access to symbolic execution and also several built-in analyses that do a lot of common tasks like control flow graph recovery, data flow analysis, etc., etc. And additionally, it has a knowledge base that allows analyses to store artifacts of truth that it has found about the program it is analyzing. So here in this example, this is just copied from our homepage. It imports angr, loads this sort of fake firmware binary, fauxware, performs a control flow graph analysis on it, and now the project's knowledge base has been populated with a listing of all the functions in the binary. For example, here's the entry point, here's the main function, here's 2 functions conveniently called accepted and rejected, etc., etc. And then we create an abstraction called a path group, which is a control interface for symbolic execution, and tell the path group to just blindly tick forward until it finds any state that lives at this address, which is conveniently, I'm pretty sure this hex address is the same as this accepted state address in hex. So we just search for a state at that address, and then when we find one of those states, we ask for a concretization of standard input, and it tells us the password for this firmware. So that's that example. That's just the fauxware example. That's the tour de force of here's angr doing static analysis and symbolic execution really fast. That was a lot. Angr is big and complicated, but a lot of care has been taken to make it a stack of useful abstractions so that any part of the binary analysis process can be easily instrumented. And what can we do with angr? Well, we can analyze a lot of things. We can do symbolic execution, as I've shown. There's lots of built-in analyses that ship with angr. Control flow graph, binary diffing, disassembly, backward slicing, data flow analysis, value set analysis, etc. We wrote and then published on a static binary rewriter that can do reassembly of binary programs with instrumentation. There's some limited ability to do type inference. We can do symbolically assisted fuzzing, which is very good for bug finding. We can do automatic exploit generation. And also, if you're us, you can use angr to build a huge system to play an automated form to play CTF automatically and win 3rd place in the world's first automated CTF called the Cyber Grand Challenge. Oh god, I need to talk about the CGC now. So, how much time do I have? I've only used 15 minutes. Okay, I can talk about the CGC. So, in the United States of America, there's this part of the government called DARPA, and their job is to throw a lot of money at researchers to do research that they want to do. So, one of the things that they've done recently is they decided, well, we want the state-of-the-art for binary analysis and auto exploitation, etc., to be advanced. So they said, hey, researchers in the United States, we want you to build a machine that can play against other machines totally autonomously, playing the standard game that we call capture the flag. Now, this is sort of a format that DARPA has done in the past. DARPA, their original grand challenge was for self-driving cars. You may have heard of that. The grand challenge was, let's take this established human sport of car racing and say, can we build AIs to do the same thing? And so the Cyber Grand Challenge is the same thing, but for the game of CTF. So this ultimately turned into a huge engineering effort of there's a lot of trauma associated with the 4 months of horrifying development that went into the CGC, but ultimately we built a system called the mechanical fish to use angr at its core to analyze binaries, find vulnerabilities, and then patch those vulnerabilities, turn the vulnerabilities into exploits, and then launch those exploits against a series of opponents on a closed network, and win us $1.5 million. That was pretty good. This is all open source. The angr is totally open source. All of the mechanical fish is also open source, I should mention. It's just sort of sitting up on GitHub. If you wanted to kickstart a robot uprising, it's probably a good place to start. So there's some of the analysis capabilities of angr, but what you can also do is build a community. Well, that's what we've done. It's because a lot of people seem to be using angr for some reason, and we've got 100 people idling on our IRC channel, and got over 100 people on our Slack channel asking questions about why did my script break, and we've got a really nice community on GitHub talk where people are submitting pull requests, opening issues, and people are servicing pull requests that aren't the core research team in the Sec Lab, and it's mind-boggling that people do this for us. And what we've also done is we've also made friends with other open source projects that we use. For example, Z3, Capstone, Unicorn Engine, Creamer. I've mostly made patches to those systems and then submitted them and had them accepted. And for some of these, for Z3, Capstone, well, not quite Capstone yet, Capstone's being finalized, but Unicorn Engine, I manage package distribution for some of those things. So we're making friends. We're doing lots of good things out in the open source world, so that's fun. And ultimately, all this is possible because we can lift binary code to VEX and execute it symbolically. That's the primary operation down here. But we started building angr. I shouldn't say we. I like taking credit for all of these things, but angr was started before I came into the Sec Lab around 2013. And when I started building angr, the question was, well, what analysis IR do you actually want to use? So that's part 2 of this talk, which is a brief summary of other analysis IRs. First up is BAP, the Binary Analysis Platform, which is an IR that comes out of CMU, Carnegie Mellon University, also in the United States, for their research. Most notably, their bug-finding tool called Mayhem is powered by BAP. As a brief side note, CMU was originally using VEX, but they were completely unable to deal with implementing all the clean helpers and dirty helpers, so they made their own lifter. And also important to note that CMU Research's spin-off company, For All Secure, won first place in the CGC. They kicked our asses. Not by much, though. We published an interesting paper looking at the actual gameplay of the CGC and saw politics. So the BAP is pretty cool. It's written in OCaml by people who actually have a background in program analysis. So it's got some cool stuff in it, but on the other hand, it's written in OCaml. And the IR is tied to the larger binary analysis platform that they use. And even furthermore, it only supports Intel and ARM, and I'm not even sure if it supports ARM64. And Furthermore, when they started angr in 2013, BAP was very heavily fragmented and required a copy of their code base in your tree in order to use. But since then, it has been totally rewritten, so it's a little better now. If you wanted to use it, you wouldn't be totally insane. Next is Rio, not sure how to pronounce that. It's the reverse engineering intermediate language. Someone published a paper in 2009 describing the ideal binary analysis IR, which is ideal. However, it doesn't actually exist. No one really implemented it. So there is an OpenReal project that is trying to implement this for x86, but if you decide to implement a binary lifter, you will not implement an analysis platform. You will spend 3 years designing a binary lifter. So back in 2013, we're not using Real. So then there's Llvm. this is a pretty serious contender. It's the Clang IR. It is wildly popular for program analysis. We've started getting program analyst experts coming into our angr Slack and spouting Haskell at us. I'm like, all right, I sort of know what a monad is. Anyway, so Llvm is very robust, it's very established, it's very good, and there's a large community and body of knowledge about how to use it for certain analysis tasks, like various optimization tasks. And symbolic execution with Llvm is 200 lines of C++. So that's nice. But on the other hand, it's not really good for our use case. It's designed for compilers, not lifters. There's no real, it's very difficult to reason about register allocation from Llvm, and there doesn't really exist an official lifter from binary code to Llvm. It's all the other way. There's some community projects, Nsvc comes to mind by Trail of Bits, that are meant to do that, to lift binary code into Llvm. They sort of work, I guess. Last I heard, Trail of Bits has abandoned Nsvc, though don't quote me on that. And it's not, so this isn't really something that we're very interested in using for binary analysis. So then there's TCG, which is the QEMU IR. This is very good. This is what QEMU uses internally to do its optimization and JITting. And one of the really interesting things about being in QEMU is that it suddenly supports everything QEMU supports, which is everything. Everything is supported by QEMU. But then there's a problem that it's designed to be used for QEMU and nothing but QEMU. So the only implementation is just buried in the depths of QEMU that we once burned an entire intern trying to get it out. But that was weird. But no, interestingly enough, one of our colleagues in the last few months has successfully done this. So there are patches going into QEMU being talked about right around now that have to do with being able to compile QEMU as libtcg. So once that goes through, we would actually be able to run angr on other things that QEMU supports. Now there is VEX. Vexy people in the audience, does VEX stand for anything? This is very important.
This is very embarrassing. It actually stood for Valgrind Experimentals.
Valgrind Experimentals. Interesting.
It would be better if you didn't know. So.
I'll forget that, don't worry. So, good things, very good things about VEX. It's obviously got an official implementation, Libvex, there it is. And it supports tons of architectures, anything Valgrind support, that's very good. And it is designed for binary analysis and instrumentation, that's also very good. And it's written in C, so its structures are well defined and easy to export to other languages, under active development, and supports a very wide range of ISAs. Like, if you look into other analysis platforms, they've got long-running issues open for months and years about, well, we've got to support the SSE extensions to x86. Who wants to write that? Nobody. But VEX has that. That's good. There are some issues with VEX, though. It is designed for the Valgrind use case, so dynamically executing user mode programs is what it caters to. So, and then furthermore, there's no real way to get the IR out of Libvex. The Libvex workflow is just this one function, libvex_translate, which does this entire pipeline that Julian had on the screen earlier of lift, instrument, optimize, code gen. And we only really care about the first part of that. We only really care about the lifting. So for a while we had this really janky solution that commented out half of Libvex translate and then used one of the instrumentation functions to deep copy out the IRSB. I fixed that recently. That's good. Furthermore, you do have to implement a billion IROPS and C calls, and some of them are pretty weird. Like there's IROPS for floating point, sine and cosine, etc. And furthermore, it's not really SSA. Julian talked about this in the previous talk as well. The IR has no interconnectivity of control flow. There's no ability to reason with just the IR about control flow. And furthermore, from a real SSA IR, you want the memory writes and register writes to also be single static assignments. I'm talking some pretty nasty program analysis stuff, so sorry if this is going over people's heads. But none of these are showstoppers, and that's the important thing. VEX is the one that we want to use, and VEX is the one that we ended up using. So that's what the next part of the talk about. That's what the next part of the talk is about. Words. So what did we do? We forked VEX. There's our fork of VEX sitting at github.com/angr/VEX, and makes a lot of changes to it. And I'm not going to lie, a big part of me giving this talk is me being able to be in the same room as a lot of Valgrind people so we can pitch a whole lot of changes we want to upstream to VEX. There's a lot of them. This is the part where things are going to get very, very technical. So if you're not interested in the specific lines of VEX/priv/guest arm2ir.c, this might be a little weird. So ultimately, so I talked about the issue of the whole gigantic libvex translate function. So what we did is we split it into two functions, lift and codegen. There's still the libvex translate function that just calls one and then the other. We've made sure to maintain all the interfaces, so theoretically you could just merge these in Valgrind and we could still totally continue working. I haven't tested this, which means it's broken. But yeah. So then there's the problem that libvex's multi-arch mode doesn't actually work, which is to say that there's this idea of VEX that it can lift from any host and compile to lift from any guest and compile to any host, and this will all magically work, and it really, really, really doesn't. Oh, I've got some good news about you about some patches we'd like to upstream. And furthermore, there's a lot of assumptions made in various parts of various lifters that the host is the same as the guest, and that's nasty. So we have patches for that. Furthermore, we'd like to be able to use angr to analyze things that aren't just userland program. We had a project a few years ago, about analyzing some x86 firmware. So we have some patches that make it feasible to analyze real mode programs in x86. And then one of the final things that we want to do is just sort of generally improve the meta properties of the IR that dynamic execution ignores, but static execution really, really needs. Like, for example, making sure that all the jump kinds are always accurate. So at the end of each VEX block, when you translate from one block of VEX IR to another block of VEX IR, there is a jump kind, which is what kind of jump is it? Is it a boring jump? Is it a function call? Is it a function return? Is it a syscall? What do you want to do? So that's not really necessary if you're just executing through the code, but once you're performing analysis on it, you need to sort of start keeping track of what function you're in. It's very important that that's right all the time. So there's a couple of cases where that was wrong, and now it's right.
Is it even really knowable?
Nothing is ever really knowable.
Yep, but seriously. Some of the jump kinds, particularly the spot function returns, are impossible to. It's like we really love to know that, because then we can make Cauldron work on all platforms. But it seems to me impossible to know. Yeah,
there's actually currently an issue open on our end about one of our post processors that is overzealous about at marking something as a return. So we need a better heuristic for that. But all the patches that I'm about to present are good as far as we know. They're strictly better.
Okay, let me not distract you.
Yeah. So let's take a look. I'm going to run that huge bash command, and we're going to cycle through all the commits, all 30 of them, and we're going to take a look at what exactly I've done. Please tell me that's in my history. Please. Okay, I guess I can just copy that. I'm glad I kept it around. Hang on. Yeah, that's the one. Anyway, so we use Git, not SVN, because we love ourselves. So our first commit in our repository is just importing our 3299 at SVN. This is that was the most recent commit as of about a week ago. I rebased everything on top of the current master, so this should all be good. So this is just import of VEX into Git. So the next thing we do is just adding a get, ignore, and readme, and
That one character, move the terminal that one character to the right. So
it's important. Hang on. Good. All right. First off, TileGX doesn't work in multi-arch mode for some reason. The make file just sitting in the VEX repository seems to have been not updated in a very long time. It doesn't even include the object files for the TileGX code. Yeah. Yeah, and I was looking at those messages and I'm like, maybe I shouldn't put in the effort to support this. So disable TileGX in multi-arch mode. Second one, in x86 it's important we switch these LDT and GDT registers from being H words to being Llvms. The goal is that they take up a consistent amount of space regardless of the regardless of the host architecture. And this is important because we have a static mapping in angr of all of the offsets in the guest register file, and we'd like to not have to have some magic way of updating that depending on what your analysis platform is. Next, we clean up the build system. This is just a big cleanup of the Libvex build system. It is big and it is clean and it paves the way. And oh, this is actually an important change I should go over. Where's the gen offsets program? Right. So there's this public. Look, I'm doing my best. So there's this program called gen offsets in the Libvex build process, which generates this public header, pub/libvex_guest_offsets.h. And the idea is to hold on to have there be a public record of what the actual offsets into the host file, into the guest register files are. Like, what offsets do you need to look into the register file to find EAX, or R0 on ARM, or R0 on PowerPC? Previously, there was a real hacked up grep into sed into something to make everything work, but because of that change that we just made, the one with changing the H words to the Llvms, now everything is consistent across every platform, and we can use something much simpler in order to actually grab those offsets. In this case, it just compile a program that includes that just runs the size of macro a billion times and dumps them all out into that header file.
Does this work even when cross-compiling?
Huh?
Does this work even when cross-compiling?
Yes, that's the idea.
Right, that's good. Okay.
Next, support compiling for Windows via Nsvc. This was not fun. It's a lot. It's basically a whole bunch of. The real kicker is def. We condition out a whole bunch of weird varargs code with another version that Nsvc understands. Okay, then here's the stuff where we just do a bunch of defines to stub out all the GCC specific functionality. I got it to work at one point, and then my Windows machine fell over and died, so I'm not really sure how well it works right now. But it worked, and it can probably work given about 30 minutes of dead time, and a working Windows machine. And then there's just a whole bunch of things about, for example, Nsvc can't handle empty anonymous structs, so et cetera, et cetera. Just a bunch of random hacks like that. It shouldn't be any overhead. It's just weird stuff. Next is we replace. There's this adder type, which is this generic host word that sort of switches between 62 and 32 bits based on the architecture. That's no good, because then you can't analyze 64-bit from a 32-bit host.
Yeah, that's pollution. It should never have got in there. That's
Yeah. So we just, and this is a bit of a hack. It should probably be addressed more carefully, but for the time being, it just needs to be 64 wide. Next, we add a function called Libvex update control. There's this Vex control struct, which is sort of a global variable floating around Vex that adds the ability to have these sort of just sort of global options for how the optimization process should work. And you're only allowed to set this once, is the problem. You set this in the libvex init function, and then you're never allowed to touch it again, which is not ideal when you want to update, for example, the maximum number of instructions that you'd like to lift. And later on in this thing, I'm going to add a couple more options, and it's useful to have them partitioned out like this. So, cool. Next is the thing I'm talking about. We split libvex translate into libvex lift and libvex codegen, so it's not a huge deal. We just here is it. You can't really see it, but libvex translate has just become just these green lines right here, which calls libvex lift, libvex codegen, return res, you're done. Not super hard. Next is we add a parameter to the vex control that is maximum number of bytes per lift. There's already a concept of maximum number of instructions per lift, but we would also like to be able to have a maximum number of bytes per lift. Useful. Furthermore, there are a lot of weird optimizations that happen in the lifting process, which have negative effects on analysis. For example, in the ARM mode, in the ARM thumb mode lifting, it tries to do this look back behind the current instructions to see if any of them could have been a conditional instruction, and if they're not, it means you can optimize the hell out of that code. However, there's use cases from Pyvex that doesn't make sense, where there doesn't exist code behind the current code, there's not a continuous mapping of just the code segments. So we need to be able to disable that behavior. So then previously the ARM lifter's endness was dependent on the host, which doesn't really make a whole lot of sense. So now we're dealing with the guests. And furthermore, involves just some changes to make sure that you you pull words out of memory with the correct endness, etc., etc. Next, I have no idea why this code ever works, but here it is. At some point, you just take the guest access, cast it to a host pointer, and try dereferencing it. And that makes absolutely no sense, so here's a fix.
Can I make a suggestion?
Yes.
This is a lot of relatively small changes.
Yes.
Did you want to talk also, because time is limited,
yeah.
talk also about changing the IR? Mm-hmm. That's a much harder problem. I mean, this is like, largely it's no big deal.
Yeah, there are no real changes to the IR. We like VEX a lot. We like the way it is, and we don't have any solutions for sort of the architectural problems.
Said, for example, it doesn't give any real representation of what happens in between basic blocks.
We don't have an answer for that.
I thought you'd have this.
Yeah. No. God. No. I wish. Yeah. I guess I can talk about this more in sort of terms of general patterns that Valgrind doesn't support, but we would like to. For example, there's previously the assertion that when you have a service call, a syscall on ARM, the service call number must be 0, and when you're analyzing weird firmware, that's not always the case.
I mean, there's a lot of small changes.
Yeah, a lot of small changes. So, yeah.
It's really the architecture level stuff which is hard to do. I mean, the top level structure.
Yeah. I think at this point I've explained all the structural changes. I stuck those pretty early in the commit history. If you've been watching the dates, they've been jumping back and forth and back and forth and back and forth. What's something structural that we can talk about? MIPS to...
So, can I ask you a maybe different question, which is, if you actually just shove this lot into the standard Valgrind, does it still work?
I haven't tried it, but it should. It really should, because I'll... Yeah. I took some care to make sure that all the interfaces were preserved and that any new options that I added defaulted to the original behavior. So, let's see, anything else that's interesting? Anything interesting? Blah, blah, blah. Blah. Okay, then this is a huge commit that adds support for analyzing x86 real mode code. So we add a parameter to the archinfo that is the CR0 x86 register. And so that controls a big chunk of the new x86 lifting logic. And also involves handling the LDT, GDT registers correctly, and it's just reorganization. It's pretty fundamental and sort of needs to drive home the idea that VEX has uses outside of analyzing real mode programs dynamically. So, optimization, and there's a weird type error I found. And that's all 30 commits. So, go back to here. That was a lot. That was a lot less than it could have been. I spent the last 2 weeks cleaning up our 3 years of mess of commit history and packaging it into this series of 30 meaningful patches. So I have put in a lot of work to make this nice and hopefully just ready to be accepted given some testing. So some future ideas that are, these are some more architectural, some architectural, some structural changes. My understanding is that the origin of the C calls in VEX are that they were originally copied from QEMU. I don't know how true this is, but the idea that there's some, for example, when VEX wants to calculate the E flags for an x86 jump instruction, like so in x86 you can say jump if less than or equal to, and what that actually does is it checks just a bit in the condition flags that get set every time you do a math operation. And so VEX doesn't want to recalculate those condition flags every single instruction, so it saves off the operators and the operand for every math instruction it does. All the unnecessary ones get filtered out by the optimizer. And then when it actually sees that it needs to calculate the bits of the E flags register, it calls out to this sort of external function which magically knows how to take the operation and the operands and return whether the branch passes or not. So, and it's totally possible that and the existence of these C calls is a hindrance to analysis and optimization and lots of things. So it would be nice in the future if we could inline all these C calls as just IR. Furthermore, having there be thread safety in Libvex would be very, 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 very nice, because I mean, we're in Python, so it doesn't make a whole lot of difference, but there are many applications for us which live mostly in Libvex. For example, we do have a rock chain generator that most of its lifetime is spent in Libvex. So if we could multi-thread that, it would be very, very, very fast. This is hard because VEX is designed to make zero assumptions about its outside model. So it has no access to anything that could possibly give it thread local storage. So there would probably end up being a callback that it would call that it's just saying, hey, whoever's invoking me, please give me my thread local storage block, and it would do that. But that would involve moving literally every single global in Libvex into that huge thread local storage struct. So it's hard, but it would be useful and it would require a lot of refactoring. So multi-arch mode works, at least now, from a little endian host. We've tested this pretty extensively from 32-bit and 64-bit little endian hosts. You can lift without faults all architectures. We haven't tested this with big endian hosts, and my feeling is that it's going to fail if you try to lift some x86 on a MIPS processor. Et cetera, et cetera, et cetera. That's not important. This is very urgent. The indentation in Libvex is 3 spaces. That feels like some sort of joke. And 1 space would be better than 3 spaces, honestly.
So we need to discuss what color to paint the bike show.
Yeah. So on a separate note, on a less joke-filled note, licensing is a bit of an issue. So Libvex is GPL. This is a little scary because we don't want angr to be GPL. Our university wants angr, it wants all code to be BSD. And we have this belief that we've sufficiently insulated ourselves from dependency on Libvex through having there be multiple lifter backends to PyVex, having no real strict dependency on the exact list of enums that come out of Libvex. But in the end, it ends up being this weird legal question of what does the GPL cover? Does the GPL cover the implementation of Libvex, or does the GPL cover the concept of the VEX IR? And we really don't want to find out the answer to that question. So the easiest thing we think would be for there to be there's this library license exception, runtime library exception that gets added to Libc, for example, which is GPL, but there's no, but just because you link with Libc doesn't mean that you're required for your program to also be GPL. So that's probably something that needs to be discussed in depth, but that's an important issue that's important to the livelihood of angr and me. So that's pretty much it. That's the angr project. That's our interactions with Libvex, and that's me being funny on stage for an hour. I will be glad to take any questions that you have. Questions?
So the jumps programs that you have, I understand that it's hard to know, sometimes impossible. But is it mostly because of optimizations and mainlining, or is there anything else more fundamental that would stop you from knowing how to go back? Because he said that you need more information. He said that you can't need it, and now I'm just trying to understand the logic.
So the nightmare case is on ARM and thumb. There's no such thing as a ret instruction. There's just this weird instruction which pops a number of things off of the stack and puts them into various registers, and this can include the program counter. So
Dozens of ways to return.
Yeah.
Yes.
Yeah.
So it's just, but that's like a return, right?
Yeah.
BC.
Yeah. So that's the heuristic that we tried to implement, and it's not. I'm the exact issue that's coming up isn't right, but
So it's not a CFG problem. It's an instruction problem.
it's an instruction problem.
That's easier to solve.
I think there are some CFG problems, but like
No, there probably is.
yes, absolutely.
Those are the impossible ones to solve. To start with.
I think I'm not the person who deals with CFG. That's a very, 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 very smart person named Fish, a PhD student in our lab.
Fish name first.
Yeah. We have lots of code. We have a very complicated control flow recovery algorithm. I'm pretty sure there are considerations for the CFG-based cases in there. So, but of course nothing's perfect. Everything's unknowable. Anything else?
How do you deal with syscall restrictions or memory locations that depends on things you might not know, for example?
Yeah. So you mentioned memory locations. This is a general problem in symbolic execution. What do you do when you have a store to a memory address that's symbolic? And the answer is we give you a lot of tools to decide what to do. So you can either concretize the memory storage address, you can concretize it to a range of possible addresses and store conditionally to all of them, the less tractable it is. This is an open question to what's the best way to do it, and there's lots of publication on what to do it, and we sort of try to provide everything that you can so you can pick what you need to do with your analysis. That's why we call angr a suite.
So you can access tools to do that with angr? You can access tools to choose something to do with angr about that?
Yeah. Any question? Oh, wait, hang on. You mentioned syscalls. We're in the middle of refactoring the precise relationship between an angr or program running in angr and its environment, but the idea is that oh boy. So I mentioned that SymVex can do things other than just execute vex. Well, one of them is execute a syscall. And so the main top-level loop is, well, if we see that the previous jump kind is ijk sys, instead of running vex, we run the syscall engine, and then the next time we see that it's time to execute more vex.
It depends on the actual context you're running your your relation.
Yeah.
It's basically how do you because it's static analysis. So if you have, for example, read syscolon, something that does not exist at the analysis time.
So you're talking about, like, for example, what does the open file syscall do?
Yeah, for example.
It just creates the idea that, well, there's two cases. Either the open succeeded and it didn't. If it didn't succeed, you can create a successor state with a failure state. And if it did succeed, you create a concept of an open file with unknown contents, symbolic contents, so that so it will return a file descriptor, and then anytime you read off that file descriptor, it will return symbolic data and also the possibility of EOF.
So basically, you also emulate the operating system.
It's big. I mean, this is a project we've been doing basically nonstop for the last 4 years. It's big.
About your S17 coding, how do you handle floating point numbers?
Z3 has primitive support for floating point numbers. It does work. It's very, very, very buggy. We found numerous seg faults in Z3 we were unable to track down to a root cause. So sometimes what we do is, I think the approach that we took during the CGC for maximum resiliency was every time we see a floating point operation, we just say, throw up our hands, nothing we can do, concretize any symbolic values that turn into floating point, and then every time we see an actual operation, we just turn them into Python floats, add them, put them back into bit vectors. So then this maintains tractability, and usually when there's bugs, they don't often come from floating point nonsense. If we wanted to really put our if Z3 works, then we could just put everything through Z3's symbolic IEEE 754.
Yeah, I work with Z3 as well.
Okay.
And recently I found this soft SMT something called MATSAT. It's much better than Z3, so maybe you can guys.
Yeah, there's an interesting amount of research out there about for frameworks like this, which just want a solution to something. What you can just do is you can spin up any number of SAT solvers in parallel and just use the one of whichever one returns first. Use the result. So that's an approach that we've wanted to implement for a while using. Which one did you say was good?
MATSAT.
MATSAT.
Yeah.
Interesting. Okay, thank you very much. Anything else? That will be all.